So let's see how these properties of QR factorizations make our lives easier. Well, remember that one of the properties in a QR factorization is that the columns of Q form an orthonormal basis of the column space of A. So now we get a new theorem. When A equals Q times R, it turns out that we can easily calculate the projection matrix onto the column space of A with the formula projection matrix onto the column space of A equals Q times Q transpose. And for the proof of this theorem, remember that the columns of Q form a basis of the column space of A when we have a QR factorization. So I can apply the projection formula, which is usually x times the inverse of the gramian of x times x transpose, where x is any matrix whose columns form a basis of the column space of A. But since the columns of Q form an orthonormal basis of the column space of A, I can use x equals Q in the projection formula. So now I'm looking at Q times the inverse of the gramian of Q times Q transpose. But the beauty of this is that the gramian of Q is the identity matrix because this is a QR factorization and Q has to have orthonormal columns. So now the hard part of a projection problem is normally inverting this middle matrix, the gramian. But since the gramian here is already equal to the identity, I don't need to do any inversion. So this just collapses to Q times Q transpose, which is much easier to calculate than the normal projection formula. So, and that's the entire proof of the theorem. So we now have an advantage. We have two projection formulas, so to say. If you don't have a QR factorization, you'd have to go through the whole calculation from scratch. To calculate the projection onto the column space of A, you'd have to find a basis of the column space of A, put that basis into the columns of a matrix called X, and then apply the projection formula, and the gross part of that calculation is inverting the gramian of X. But if someone is kind enough to give you a QR factorization, our previous theorem says, forget the original projection formula, all you really need to do is multiply Q times Q transpose, which is much faster and much easier than the normal projection problem. So we avoid the difficult inversion of the gramian of X when we have a QR factorization. And this is why numerical math, or people who work in numerics, love QR factorizations because they make calculations much faster. So let's look at an example here. Here I have a 4x3 matrix A factored as Q times R. So again, by saying this is a QR factorization, what I'm implicitly telling you is that the columns of Q here are orthonormal, meaning that Q transpose times Q is the identity matrix. Well, let's say that I wanted to find projection onto the column space of A. What our theorem is telling us is that projection onto the column space of A is given by multiplying Q times its transpose on the right. And the cool thing about this is we know Q transpose times Q is the identity, but Q times Q transpose is not the identity because Q is not invertible here because it's not square. Here, Q times Q transpose is projection onto the column space of A, and I did the calculation and got this 4x4 matrix when I multiplied Q by Q transpose. The point here is that I don't have to do an ugly calculation to find the projection matrix here because someone is giving me a QR factorization. If someone just gave me A, I'd have to find a basis of the column space of A. I'd have to put that basis into the columns of a matrix called X. That matrix X is almost guaranteed to not have orthonormal columns. So I'd have to invert the gramian as part of my projection calculation, which is a lot of work. Instead, here, someone was nice enough to give us a QR factorization, so solving the projection problem is almost immediate.